Imagine a big Lego castle. The picture on the box that shows the whole castle, this is the conceptual view. The small Lego instruction booklet that each kid gets, this is the external view. The actual plastic bricks stored in the box, this is the internal view. The three schema architecture separates what the whole system means, how each user or program sees it, and how it is really stored on disk. This separation keeps the system flexible. You can change the bricks internal without changing the picture conceptual, and you can give each kid a different instruction booklet external without touching the other parts. An external schema, also called a user view, is like a personal window that shows only the part of the database a user cares about. For example, in a school database, a teacher might see a view with columns student ID, name, grade, while the principal's view also includes attendance and disciplinary notes. The view is defined with a select statement. For example, create view teacher view as select student ID, name, grade from students. The database stores this definition, not the actual data, so the same physical tables can serve many different windows. This lets each user work with simple, familiar tables without seeing the whole complex underlying structure. The conceptual schema is the logical blueprint of the whole database, like a city map that shows all streets, parks, and buildings, but not the materials of the roads. In a relational DBMS, it is a collection of tables, their attributes, primary keys, foreign keys, and integrity rules. Example, a student table with attributes student ID, name, age. Major, where student ID is the primary key, and major must exist in the department table foreign key. Integrity constraints are expressed as logical formulas. For example, for all S, student of S implies age of S greater than or equal to 0. Relational algebra lets us query this model. Sigma age greater than 18 of students selects adult students, pi name and major of student projects just names and majors, and gamma major and count of all groups by major. These algebraic expressions are independent of how data is stored on disk. The internal schema describes how the logical tables are really kept on the hard drive, like the exact arrangement of Lego bricks in the box. Data is stored in pages which are fixed size blocks, for example 8 kilobytes. A tuple, a row size t is t, equals the sum of the sizes of attribute I. If a table has n rows, the offset of row r in a page is offset equals base page address plus r times t. Indexes, for example b plus trees, are extra structures that point to the pages, speeding up search. A B plus tree node can hold about the floor of page size minus header, divided by key size plus pointer size keys. By arranging data this way, the DBMS can retrieve a row with only a few input-output operations, instead of scanning the whole file. Mapping between schemas is written as mathematical functions. An external to conceptual mapping, F sub EC:(E) maps, to C translates each user view attribute to its source table attribute. For a view V of student name and grade, we have F sub EC of student name equals student.name, and F sub EC of grade equals enrollment.grade. The conceptual to internal mapping G sub CI:(C) maps to I defines how each logical column is laid out on disk. For example, G sub CI of student.age equals page ID, offset. Formally, a tuple T belongs to C is transformed to a physical record R equals G sub CI of T. These functions are stored in system catalogs and used by the optimizer to rewrite queries from the external level down to the internal level. Data independence means you can change one level without breaking the others. Logical independence lets you add a new attribute to a table without affecting existing user views. Example, add email to student. The view teacher view still works because it does not reference email. The DBMS rewrites the view query select student ID, name, grade from students to select student ID, name, grade from students unchanged. Physical independence lets you move a table to a different storage device or change the indexing method. The logical query select all from student where student ID equals 123 stays the same. The optimizer rewrites it to use the new index, like turning a table scan into an index seek. Select all from student where student ID equals 123 becomes index seek of student ID equals 123. This shows that users never see the physical details. The DBMS keeps all schema definitions in a metadata catalog, also called the data dictionary. Think of it as a library catalog that tells you where every book is. The catalog has tables like tables, columns, views, and indexes. DDL statements create table, create view are stored as rows in these tables. A view definition language VDL stores the text of each view. For example, view_def equals select student ID name from students. The catalog hierarchy often has 3 layers. System level stores DBMS objects, user level stores user-defined tables and views, and application level stores temporary or session objects. The DBMS reads the catalog whenever it parses a query to know how to translate names into physical locations. When a query touches several schema levels, the optimizer must estimate the cost. Cost equals sigma I slash O sub I times C underscore IO plus sigma CPU sub J times C underscore CPU. Where I slash O sub I is the number of page reads and writes for operation I and C underscore IO is the cost per I slash O. CPU sub J counts CPU operations, for example hash joins, with cost C underscore CPU. Cross-schema optimization can push selections from the external view down to the internal level. Predicate push down, reducing I slash O. For example, a view V that filters age greater than 30 can be merged with the base table scan, so that only matching pages are read. The optimizer uses statistics stored in the catalog, row counts, selectivity, to compute I slash O sub I and choose the cheapest plan. Case study online bookstore. External schemas create views for different roles. Customer view with books price availability, admin view with orders inventory supplier info. Example, create view customer view as select book ID, title, price, stock from books. Conceptual schema, define tables books with book ID primary key, title, author, price, stock. Orders with order ID primary key, customer ID foreign key, book ID foreign key, quantity, suppliers with supplier ID primary key name. Add integrity rules. Quantity greater than 0, stock greater than or equal to 0, foreign key constraints. Internal schema, decide page size 8 kilobytes, store books as clustered B plus tree on book ID. Create secondary index on price for fast price range queries. Compute tuple size, T equals 4 plus 50 plus 30 plus 8 plus 4 approximately 96 bytes. Mapping F sub EC of customer view title equals books title. G sub CI of books price equals page ID offset. Data independence, later add column genre to books. No view changes, optimizer updates internal layout without affecting queries. Catalog entries in tables for each table, columns for each attribute, views storing the select text, indexes storing index type and key columns. Optimization, a query select title from customer view where price less than 20 is rewritten to select title from books where price less than 20. Using the price index, cost equals log base B of n times CIO instead of a full table scan. Deployment, load data, create views, define indexes, gather statistics, and enable the optimizer. The 3-level schema lets developers modify storage or add new views without breaking existing application code.